to ease of generation. So we've got fluent meshing, we've got Ansys meshing as well. We do have ISIM, but we won't look at that in this particular case. What I wanted to point out with here is kind of the ease of generation, right? So in both these settings, and we'll have a look through them a little bit later on, we've got these, under the mesh, we've got all these different conditions and these components that have been created, giving us information about things like the edge sizing, body sizing, how we've actually generated this mesh. What it allows us to do, it allows us to regenerate the mesh easily based off features and name selection as well. Fluent meshing, the interface is a little bit different. There are some benefits to the different softwares as well. But similar way, we've got a kind of step-by-step process to go through what we can do, how to actually generate the mesh, and then how we can generate the subsequent meshes as well. So talking a little bit about efficiency, this is a simplified way of how I look at it, right? The two meshing approaches that we've got, Ansys meshing, I primarily use it for simpler geometries. The mesh types that it's actually able to generate are prisms, pyramids, hex, and tets. When it comes to generating them, we can use parallel meshing when it generates the prisms. So that's the inflation elements. We'll talk about inflation and prisms and the terminology a little bit later. But the geometry has to be watertight. So we have to have, extracted the enclosure, right? Fluent meshing, on the other hand, it's more robust, right? We use it for a lot more complicated geometry. We can generate more meshing elements, more topology. So prisms, pyramids, hexahedrals. We've also got polyhedrals that we can generate, a hex core, which has hex elements, which has nice hex elements internally. We'll look at that a little bit later on, and polyhex core as well. On the parallel meshing side of things, so the prisms, tets, and polys and the polyhex core are all parallelized. So it means that we can actually, run them a lot quicker as well. And then in fluent meshing, we can bring in watertight geometry, but we can also bring in dirty geometry, right? So geometry where we haven't actually extracted the volume. And we've got a bit of an explanation and a bit of a demo a little bit later showing you what you can do. And we've got what's called a fault-tolerant workflow, which walks through that. So, I talked about what does mesh mean to be parallel, right? It just means instead of using a single core to generate the mesh, we can use multiple cores on our actual machine. So I've got a 4-core machine on my laptop. That being said, if you guys have clusters, we've got a lot more. Cores that we can use. You can see here as the number of cores kind of increases. So as we go to the right, the actual speed, so the blue line, starts to increase as well. So the more cores we actually use, the quicker it is to actually generate that mesh. Right, and look, in this particular case, so what do we have here? It's a 3.1 million polyhex core mesh. You can see with a single core, it takes around 73 minutes, so over an hour. Whereas if you had something like 64 cores, again, it just takes around 7 minutes, right? So there's a considerable speed up as well. When we also think about efficiency, the thing we've got to keep in mind though is that coarser meshes run faster, right? So again, we're always thinking about we've got some sort of deadline. So sometimes it might make sense to, when you start the design process, to run some initial runs with a coarse mesh just so you can get an understanding, and then you can use a finer mesh to really zone in or hone in on a couple of key features if you need to, right? So that's generally the process that we start with. So start with something that's relatively coarse, get everything going, have a look at the flow features and start to refine around areas of interest. So if you have things like high pressure gradients or temperature gradients that you need to capture, we'll talk about this later on as well, but we can use what's called bodies of influence. So we can locally refine the mesh around specific volumes. So one thing we want to keep into account as well is that the more elements that we actually have, the larger amount of RAM that we need, right? So generally a TET plus a Prism grid takes around 3 GB of RAM for around 1 million elements, right? So that's another factor that you have to think about. How much RAM does my computer have? If I have an 8 or a 16 GB, stick in my computer compared to clusters that might have hundreds, that's going to change the way you think about your meshing strategy, how much RAM, how much mesh you can actually fit into these types of components as well. So this is, I've got a little bit of a case study that I wanted to go over. This is a front wing, and I've got 4 different meshes that I've actually generated, right? So this is using fluent meshing. So on the top left, we're looking at the surface mesh at the moment. I've got the next slide, which kind of takes a section through and looks through the actual volume. But at the top, you can see that we've got these polyhedral elements, and at the bottom, you can see we've got these TET elements. You'll notice, around the wing, we've got a very fine mesh. We've got some flow structures that are going to be shedding from here. So again, around this region, we've got a local refinement, but then, far away from the actual model, it gets relatively coarse, right? Because there's not really much happening around that region. So again, what I did to start with though is I started with, no refinement. I just made sure I captured some of these features, and then you can progressively start to make the mesh finer and finer to understand how fine does it need to be. So the reason I did this study was just to show you as well, the different mesh types that are available and what the actual benefits can be. So again, this is taking a cut through the middle. You can see the hex core on the left-hand side has these hex elements inside, right? On the surface, you can see we've got either TET elements for the regular hex core, or we've got these polyhedral elements, right? We've still got these prism layers, and the prism layers are used to capture the actual boundary layer as well. And again, on the right hand side, you'll notice the poly just has poly elements in the volume fill, and the tetrahedral have TET elements in the actual in the volume fill as well, right? So a couple of things though, having a look at the actual results. So this was actually done on my computer, 32 gigs of RAM, Windows 10, it's an i7, right? Nothing too special. You'll see on the left-hand side for the exact same mesh sizing, the poly hex core, has considerably less elements, around 1.3, compared to the tetrahedron, which has around 7 million, right? Having a look at the run times, right? Again, to run, I think it was around 200 iterations, which is when all of them kind of flatlined. We found that, the polyhex core took around half an hour, whereas the TETs took around 1.6. And when it comes to RAM, right, again, when we think about efficiency and computational efficiency, we're not just thinking about how long it takes to run it. We're also thinking about how much RAM that we have. You can see here, again, it takes around 8.6 gigabytes of RAM for the polyhex core, whereas the TETs took around, 25, right? So it gives you a good indication about, there are different mesh types, but at the same time, there are different reasons why you might want to go with a particular mesh type and not the other as well. There's no, easy way to figure out exactly what's going to work for you. So what you'll need to do is run your own kind of study. So I've got someone here that's saying that they can't see my screen. Is anyone else having that problem as well? Is it unpull? No, everyone's okay? Okay, I'll make sure to send them a recording afterwards then, and they can see everything. Awesome. Thanks everyone. Cool. All right, so continuing on this though, I'm showing you all these things. What happens though, right? Where are the trade-offs? And there's always trade-offs when it comes to generating these types of meshes and different types of topologies as well, right? Now, when it comes to these trade-offs, hex core. So those hex core jumps that you saw before, now we need to make sure the actual jump between a small cell and a large cell isn't around any areas of interest, because that can start to give us problems with the actual simulation and the results as well, right? I think about mesh as information. If we go from a small to a very large jump very quickly, we're losing information when we start to make that jump, right? The other thing about polyhedral elements is that depending on the actual geometry, we can get splitting, right? And I'll show you that a little bit later on, which sometimes means because of the curvature and because of the actual the element actually needs to be split in order to maintain the cell quality. So sometimes that means either reducing the first cell height, or sorry, increasing the first cell height, or it means making the mesh smaller. So depending on your actual geometry and what you've got, you might want to have a look at it. This is an example here of a mixer. You can see again on the left-hand side, we're going from relatively large elements to small elements, right? If there's anything major happening around this region, we might want to refine, this whole region. Because it's hex core, there are large, you can see here, it's kind of like a 1:4, right? Cell transition. You might need, a lot of elements to kind of capture what's happening around here. In Fluent, there is also, you can see here again that transition. In Fluent, we can apply a polyhedral fill between the two elements. So, instead of a size change of around 8, we've got something to around 3, so equivalent to a 1.5 growth rate. But again, this is something that we want to really look at, right? And you might need to do a test case to actually look through some of these things. So this is a wing. You can see here we've actually got the wing, and we've also got inflation elements. So again, we've got thin layers to pick up the boundary layer. And because the mesh is so coarse, you can see all this splitting on all these poly regions. So like I was saying before, what we might need to do is go back and either make the poly elements smaller, or we might need to make the mesh size, the inflation, a little bit larger, right? Or we might find that maybe instead of a polyhedral grid, maybe a tetrahedral grid might be appropriate for this particular case, right? So again, there is always trade-offs, right? And in generating your mesh strategy, you might want to think about some of these trade-offs as well. The other thing that we want to talk about is, what's actually happening with that flow. We've talked a lot about these unstructured grids, so polyhedral and tetrahedral, but we can also generate structured grids as well using something like ISOM or even in Ansys meshing as well. You can see an example at the bottom here. So we've got, again, hex elements on the left-hand side, and we've got tet elements on the right. We've got flow coming in at the top and at the bottom as well. It's coming in at different speeds. And you can see here, again, when we've got, so it's axial velocity of an inviscid co-flow jet. The TET grid has a huge amount of, well, not a huge amount, it's got diffusion, right? So the flow starts to diffuse out, right? Whereas you don't see that at all with the hex grid. However, when we start to compare flows that are coming off at a angle, right, we don't necessarily get the same amount of diffusion between the hex elements, between the actual mesh types as well. So depending on your flow situation, you might want to do a quick study to understand what mesh type is more efficient, what's quicker to run, easier to generate, and also accurate as well. The other thing with hex grid, if you're trying to create a fully structured grid, it can be very difficult to generate, so your ease of generation can come down. So you'll have to make that engineering judgment about what's appropriate for what you're trying to do. I've got a question here. What's the implications of cell splitting? So when the cells start to split, we just have a lot more elements in here that are generated, right? So it's split because it wants to keep the quality as good as it can, right? But generally what happens is that now we have, so many more elements on the mesh size, so that's, the time actually comes up. And again, you need to ask yourself, hey, do I need to make the elements smaller? Again, you need to think, you might need to rerun it. Or is it better to just have a tech grid, right? We've got a question here about which is better for two-phase flows. Again, that might be something that we want to do a quick test on. Depending on your problem, by the way, you might want to have a chat with us. So there's no easy way for me to just say this is the one that works, this is the one that doesn't. Normally, TETs are they're kind of industry standard. Everyone's used them. So if you doing like a paper and things like that, and you generate a tech grid or a hex grid, no one's going to ask any questions. If you generate a polygrid or a polyhex core, because the polyhex core is a relatively new element that Ansys has created, you might want to do some studies just to have a look at it as well. So the other thing that we want to talk about as well is the boundary layer. So the boundary layer, again, thinking about if you've got high pressure gradients, right? If you've got a wing that might be separating, or if you've got something that's happening like a heat transfer, right? We want to capture very accurately what's happening at the actual boundary layer. It's a very thin layer because that gives us a good idea about what the flow physics is going to be, right? So we've got these prism elements that we're going to be generating. There are different ways of generating that method as well, depending on exactly what you're looking for, right? And how accurate do you need to be? Generally, I start with what's called the last ratio, so on the bottom right. And we'll open up the solver and we'll open up the software, sorry, and have a look through some of that as well. The benefit is that it allows me to specify what the first prism, what the first element is, and then I can specify, what the last ratio is between the last prism element and the kind of last element that's out there as well. So it gives me a good transition. You can use things like aspect ratios or a smooth transition as well. And you've also got things like a uniform. So I generally don't use a uniform too much, but there might be reasons that you want to specify a uniform layer and grow it out that way. So talking a little bit about accuracy, again, look, there's no silver bullet when it comes to accuracy. A lot of the times, depending on what your particular case is, you'll have to do some sort of study. You talked about, sorry, question there about what Y plus is. Y plus, sorry, is what the first cell size is around here. We'll talk a little bit more about Y plus in Errol's case. But generally, it's whatever the first cell height is, and then depending on the physics, there's a bit of a indication about how large that first cell site needs to be. Right. So again, thinking about accuracy, there's no easy way for me to just tell you this is what's going to work or not. Generally, you need to do some sort of study, right? In this example, what I've done is I made a couple of meshes, but I've just shown you the two extremes. So this is a polyhex core grid. Generally, you try to keep, one thing as constant as you can. So I've tried to keep the sizing on the actual elements as similar as I can. So this is an FSAE car, by the way. And you can see the major thing that I've changed is actually the cell sizing around here. Now, in this particular case, we have vortices that are shedding and coming off into the actual flow, right? At the top, you've got the fine mesh, and you can see we've got this vortex that is shed off the end plate, and you've got a nice, clean kind of vortex structure that you can see that propagates down the car. At the bottom, because the mesh is very coarse, we're finding that the mesh is diffusing the actual vortex as well. Right. You can see here again, taking a slice plane, we've got more elements capturing that vortex structure. Again, so I think about mesh elements as information. And so we've got a lot more information capturing that structure at the top compared to what's happening at the bottom, right? And again, depending on exactly what you're trying to do, you might need to refine these structures. Are you looking at what's happening at the surface, or is something shedding off the surface, right? It can be a bit different. This is a video, so let me play this for you. I'll play this a couple of times. Right, so these are vortex structures that are being shed off the actual car. You'll notice the top has that fine mesh and the bottom has a coarse mesh. One of the things you'll pick up as well is that because these flow structures are coming down the car, what's generated at the front will affect what's happening at the back, right? So if we play it again, just keep an eye on the vortex coming off the actual end plate, comparing it between kind of the top and the bottom. If I pause it around there, you'll notice the vortex at the top. You can see, we've almost got a clear vortex over here, and we've got some additional flow structures around it. Whereas at the bottom, it looks like one kind of jumbled mesh, right? Again, coming down, we can see it looks like we're picking up additional flow structures around here at the top, whereas we can't really see that. Again, we've got one big jumbled mesh at the bottom. Right, and again, coming down the car again, we've got a lot more finer flow structures around here. So again, there's no easy way for me to just tell you this is accurate and this is it. This isn't. Generally, what we want to do is what's called a mesh independent study, right? So we've got some monitor of interest. So it might be drag, it might be downforce, or it might be, you are actually visibly looking at that vortex structure every single iteration. And we generally want to make the elements finer, right? So what I normally do is I'll normally keep something constant, right? So maybe the surface mesh might be constant, and I'll try to make the volume mesh a bit finer, right? And then start to pick up what's happening around there. If you're interested in what's happening, directly around the car, maybe you make you keep the volume mesh coarse, and then you just make the actual mesh around the car a little bit finer. Generally, the two things though will kind of come together, and you'll probably be making changes kind of consistently between the two of them. But this is again depending on what you want to do. Um, this stuff can get pretty difficult sometimes. So again, if this is something that you've run a couple of jobs and you're running some meshes and it's not quite giving you the results that you're after, come do let us know. Sometimes what can happen is that when you've got finer and finer meshes, instead of running a steady state, you can start to pick up these transient flow features as well. So just making the mesh finer isn't necessarily the correct answer as well. So the other thing that we want to talk about is quality, right? So look, there are different quality metrics out there. And often there are some, convoluted ways about determining, say, what the angle is between the centroid and the two faces as well. Generally, what we try to use for the orthogonal quality is the orthogonal quality for polyhedral elements, or the skewness quality for tetrahedral elements, right? And if we have a look at the help, there are some general recommendations for that, and it's also covered through the help as well. Right. This is just an example just to show you that sometimes your geometries might need to change depending on what you're trying to do. So in this particular case, again, if you see anything that's red, it's just bad. And then anything that's blue, it's good. And we're just looking at the orthogonal quality. This is an example where we've got some fine mesh elements, some fine inflation coming on the leading edge of an actual wing. And because we've got a sharp angle, we've got some bad quality elements around this region. What we might need to do is actually make some changes, right? So you can see on the right, instead of a sharp angle, it's coming to a chamfer. And again, we've still got some bad elements across there. And what we might need to do is start to increase the number of elements around those regions, so we can see that we've got a better distribution of quality around that region as well. So sometimes, and like we've talked about before as well, in the geometry side of things, I made some changes to the wheel because there was a sharp angle there. Sometimes we might need to make some changes to the actual geometry, just so that we can get, good quality elements in the mesher, and we can consistently run a lot of really high quality runs and get converged solutions as well. This is an example about the FSAE car that we looked at the start. We've got multiple different sizings depending on what we're trying to do. So we've got a body of influence around some key features. We've got curvature around the front wing and proximity as well. Again, we'll talk about some of what things like curvature and proximity actually are in the demo a little bit later on. We're also scoping prism layers, right? Because we want to pick up what's happening with the front wing and the actual pressure gradient. You'll notice here, the first cell height is pretty small, right? 0.002. And in this particular case, we've got 18 layers. We might need, more layers, again, depending on your Reynolds number. We've also got some additional sizings, curvature around the suspension arms, the wheels, and the chassis as well. You'll notice, by the way, we're interested in the front wing. So we've got a pretty fine size around the front wing. However, the chassis is relatively coarse because that's not necessarily what we're interested in at that particular case. So this is the overall mesh. Again, you can see similar to before. Coarse around here, not much happening around this region. Just interested in what's happening around the front wing and that wheel interaction, right? So I've got a finer mesh, around those regions, picking up the volume. Zooming in, you'll notice as well, I've got some proximity sizing. So between this edge, I'm enforcing 3 to 4 elements across there. You'll notice, by the way, on the actual wing on the left-hand side here, I've got some poly splitting, right? So that might indicate to myself, maybe I need to either make my mesh size smaller, or I need to think about what my inflation is doing. Taking a section through the middle, you can see I'm using polyhex core. So again, polyhex core, I've got polyhedral elements on the surface, and then I've got hex core elements in the far field. If I had a traditional hex core, it would be tetrahedral elements on the surface and hex elements in the far field. Right. Again, zooming in, you can see I've got quite a fine inflation. So the first layer is very fine and it grows out relatively large. And you can see again around areas of interest. So, the front nose curvature, that's where I've got quite a bit of sizings. How do you determine what the minimum size is? So generally look, like I said before, sometimes it can come down to trial and error. Looking at this, you can get a general idea depending on the size, how many elements you might want to have around there to capture the curvature, right? If I just had one big element, that might not be appropriate. So, 3 to 4 might be a good place to start. And then what I'll generally do is have a look at the actual results, right? So are the results telling me that I need to maybe refine around specific regions? And maybe you do a mesh study, right? So maybe you have initially 8 elements capturing that curvature, and then you run another simulation where you've got 16 elements capturing that curvature. You compare the results, or maybe you compare the CP on the actual wing, and you look at what's happening around that front wing and around that nose, and ask yourself, is there a large difference between these two regions? What am I interested in? Force, all right, is there a large change between downforce or drag? And you'll have to make that engineering decision. Is it appropriate? Do I need to make finer changes? How much accuracy do I actually need as well? So we've got a couple of key points, and I'll let you kind of go through it at your own point as well. A couple of things that I think are important to do a mesh study, right? I've got a link there to a blog that we've created. Again, there's no easy way just to figure out and look at a mesh and tell you what's going to work or not. You'll have to do some sort of study and refine around areas of interest. Look at what you're interested in, so forces, and then start to make a gut call about what is appropriate for what you're trying to do. Right. And again, the goal of doing all of this is that we want to be able to generate a clean mesh, and that's going to help us get a converged simulation consistently as well. Again, a couple other key points that we'll go through. So these are a little bit more technical on a couple of your projects. So some quality limits that you can have a look at, enforcing and making sure you've got small features, right? And if those small features need to be resolved, you've got a couple of elements across there as well, and using things like bodies of influence. This is an example of a refinement test or a study that you can do, right? So we've got 4 cases. We've got a couple of input conditions. It's just one, sorry, in this particular case. We're just progressively making the body of influence smaller and smaller. We might have some output conditions, so it might be coefficient of lift or drag. And we can start to measure that, and we can look at what the successive error is. And generally, you'll find that as you get smaller and smaller, the error between them should get smaller and smaller as well. I'll make sure to be updating the Learning Hub. Someone pointed out that a couple of the tutorials weren't actually there, so we did ask one of our team to update them, and we've just got the wrong one. So I'll make sure that they're updated by the end of the day, and I'll make sure to send everyone a link to them as well. And you'll notice the modules 6, 7, and 8 are great when it comes to talking about some of the actual meshes as well. And if you have a look at the meshing tutorials, we've also got some fluent meshing tutorials in there as well. All right. So what we'll do, let me just open up Learning Hub just to show you guys exactly where it is. We'll give ourselves like a 5-minute break, and then we'll come back and I'll open up the software and maybe walk through a particular example and talk through what's happening. All right. So if you go to the fluid, so you can go to the getting started here, click that, take you to the very bottom. So we've got 6, 7, and 8, which walks through that process. All right, geometry, information, and there are lecture slides as well. If you go to the very top and you go to pre-processing, fluent meshing or Ansys meshing, you can see we've also got tutorials in here as well for the different meshes that we've got available. Right, and some videos at the bottom. If you scroll to the top, you can just click on the Ansys meshing, and again, we've got everything there, and some additional tutorials are there as well. We don't have anything at the moment up here for ISOM, so If you are using ISIM for your particular project, have a bit of a chat with us. I'm sure I'll be able to find some content for you and send it your way. Okay. Um, Before we get into it, so we'll take like a 5-minute break. Before we take a break, does anyone have any questions at all? You can add them to the chat. I think I've been trying to look at the chat and go through some of the questions and kind of answer them as we've been going. I had a question about Y+, so what I'll do as well while we're here, again, Errol will go through this in a lot more detail tomorrow, so I don't want to take the limelight from him. But I'll just show you a couple of slides on the boundary layer and why it's important. So again, boundary layer, when we think about it, we've got 3 distinct regions: the viscous sublayer, the log layer, and the outer layer as well. So the viscous sublayer is very close to the wall, got this log layer, and then comes out to the outer layer. If we start to actually plot the velocity, again, we'll notice we've got a very high gradient close to the wall. And using log scales, there's some maths in the background to determine this as well. We can come to this graph here. Again, Errol will go through this in a little bit more detail. Generally, what it's trying to tell you is that there is at the bottom, we've got Y+, right, which is a non-dimensional value to predict what the first cell height layer should be, depending on the particular region that you want to actually capture, right? So what region that you want to capture, depending on your actual physics. So there are multiple ways that you can actually resolve the boundary layers. If you're not too fussed with the actual viscous layer, you can have a very large element in there. Or if you're very interested in what's happening very close to the wall, things like heat transfer, you'll have a lot of elements through there. Depending on what your actual project is, a lot of the times there are calculators out there that will determine it for you. So we've got one on our blog. Generally, you'll just tell it again, what is your Y+ target? What are you actually using, right? And is it internal or external? And then you give it some properties, right? So the velocity, length, density, and viscosity, and it will spit out what the first cell height layer should be, right? So in this particular case, it's 0.06. And then you'll need to determine how many elements that you need to you'll need to apply, right? And again, Errol's got a bit of a spill. Well, he's got a study that we'll talk through and show you guys, how you can determine how many elements are needed to pick up the boundary layer as well. So a couple more questions. Fatigue life of elements due to vibration. Omar, so no, we're not going to be discussing that, I think, in this particular case. The FEA that we've got next week is a little bit more basic. What you might want to do, Omar, is send us a message on support, and I'll be able to get some material, some fatigue material to you. I think actually, if you go on the Learning Hub and you pop over to the structural, we don't have it up at the moment. I think we do have fatigue information, so if you send it my way, we can. Yes, we'll in the demo we'll go over how to show different mesh elements and how to actually apply them as well. Is there a way to check the poly splitting other than manually checking? Not at the moment. No, it is just one of those things visually. After you always generate your mesh, you do want to have a look and go through and understand what's happening. If there are any meshing quality problems, there are ways that we can figure out, how to actually determine where the bad quality elements are as well. So we've got a question about if when you're conducting a mesh refinement study, would you first increase the surface mesh or volume mesh around the area of interest? So yeah, again, there's no easy way. There's no one size fits all. So you might need to play around with it. In this example where you've got something like the wing, right? Generally, with the wing, because the pressure gradients are very high, you'd like to be, solving a Y+ of 1. So you need to have a very thin layer and very thin boundary layer. And generally for a Y+ of 1, you might need to have 20 to 30 boundary layers in there. as well, right? And then capturing the curvature, again, you might want to start with something relatively coarse, and I'd probably start focusing around the actual surface mesh, right? Progressively making the surface mesh finer and finer, just picking up things like forces. And maybe in that particular case, you're looking at what the CP is around the wing, and you're looking at, how that might be changing, right? Then afterwards, you can do a study after you're happy that you've got a mesh that's fine enough, that's picking up, separation accurately. You then might want to have a look at the volume, and you're progressively making the mesh finer and finer. And when you resolve the volume, maybe in this particular case, you're looking at, what the vortex structures might be, right? So you might be finding, again, similar to this. So depending on what part of what you're actually focusing on, um, that's how I might approach kind of something like that. Are there videos, sorry, on the getting started? Yes, the download link which will hopefully have updated by the end of the by lunch. We'll have videos as well, so they're kind of Ansys videos. And if you hop on the Learning Hub, you go to the webinars, you can go to the online trainings and have a look at the old trainings that we've got. So yeah, you can see all that here as well. Right, so we've done quite a bit of these here and there. Presentations are there from the old ones. Question about the difference between hex core and polyhex core. So the biggest difference is, so for the hex core just means that we've got hex elements internal in the volume. Hex core will just have tetrahedral elements on the surface, whereas polyhex core will have polyhedral elements on the actual surface, right? Sometimes I know people don't quite like having tet elements because sometimes you can get poor quality pyramids which transition between the two different element types, and that can cause problems for particular applications. So again, it might be one of those things you might want to have a look at the structure, the topology of the actual elements, how is the hex elements connected, and what might be appropriate for what you're trying to do. And again, if you've got these questions and you've done a small study and you're still trying to figure it out, feel free to send us some measures on support and we'll be able to help you out. How do you decide what your target Y plus is? Again, there's no easy way to determine that. So generally for something like the wing, what you'll start to find is that what you want is a Y plus of 1 to clearly model the viscous sublayer. And sometimes there are some studies that even go down to like 0.2. Right? Depending on how accurate you actually need to get. But like we talked about, right, we're always thinking about trade-offs. So having a Y plus of 1 will have a lot of elements in there, and that'll make your run times a lot larger. What you might want to do is, again, a small study where you start off with a Y plus of 1, then you can go up to a Y plus of 30. So you're resolving the log layer and you want to compare the actual results. You might find that sometimes, the difference is very small. It might be a 0.5% difference, and you might be okay with that. There are some industries where a 0.5% is absolutely not appropriate, and you need to go, Y plus of 1 or even smaller as well. Right. Hopefully that answers your question, Angus. And are there any tutorials on overset meshing? Yes, I think we do have some overset meshing in here. I think we've got it in the dynamic meshing module. You can have a look at that as well. So we're not going to go through much of dynamic meshing, but dynamic meshing is changing the mesh, right? So you can see on the right, we've got, a reed, and if the reed is moving in or out, or we've got something like an engine, we can apply these types of tools to do that as well. And at the bottom here, we've got an overset mesh, and we've got a couple of videos as well, so you can have a look through. What is the lowest orthogonal quality, and does it depend on the model side? The orthogonal quality will simply go from kind of 0 to 1. Fluent will actually tell you if there are any problems with it, and we'll have a look at that in the demo. So you'll see that it'll say the inverse orthogonal quality needs to be at least 0.1, and generally when there are problems, it will tell you what it is. It is it just goes from 0 to 1, so no matter if your model size is a millimeter or a meter, it's a non-dimensional kind of value there. Right. Cool. Look, no more questions so far. All right, what we'll do, we will take a short break. And I'll just add this in here just so everyone knows, and I'll put this up. We'll take a short kind of 5-minute break. So we'll just look. We'll be back at 10 o'clock. Actually, it's probably easier. So my time at the moment is 9:53. So if we're back at 10 o'clock Australian Eastern Daylight Savings Time, I think that should be good. And then when we come back, I'll make sure to get open up, and we've got a couple of demos that we'll to walk through, a Ansys meshing demo as well as a Fluent meshing demo as well. Question about how to get ISOM training, send us a message on support and I'll have to dig it out and send it your way. We've got a couple of things here and there, but I'll just need to collate it and put it together. Okay. Awesome. All right. So we'll come back at 10 o'clock, 6 minutes, and we'll do that as well. We'll send the video tutorials. I think are these the webinars here. I'll put a link to the online training, the old online training that we've got. Right. And then again, you'll just register yourself here and have a look at some of the training as well. Right. All right. So we'll be back at 10 o'clock. All right. Thanks. Hey everyone. I hope everyone's back. Cool. So just one more question. Link to the download slides. So should be able to click FEA and CFD presentations here. And this presentation link. So these are the old ones. I'll update the new ones. Should check them. So these are the presentations. And yeah, everything should be here as well. So you can have a look through that. I think there have been a couple of changes that are made here and there and some updates. So when I've got all the videos out for the electromagnetics as well, I'll make sure to upload them to the webinar training. And yeah, it's got some of the turbulence modelings that we'll talk about a little bit later on as well in there. And again, some of the stuff on turbulence and the boundary layer as well. All right, so have a look at that. Cool. All right, so we will just get started on this one. So this example that we've got is a part of the training as well, right? So I'll walk through a couple of different things and show you guys what we're doing here. Right, so hopefully everyone can see that. So we did talk a little bit about Ansys meshing yesterday. We'll go into it in a little bit more detail today, though, right? So what do we have here? We've got, again, traditional, I guess not traditional, but it's the ribbon style toolbar. That context menu is sensitive as well. So if I hop on geometry, you'll see the menu kind of change. Anything you can see at the top here, I can also, if I right click, I can also apply that as well. So if I select this component, right click, insert sizing, I can also do that exactly the same way at the top. Just comes down to how exactly you'd like to do all of that stuff as well, right? We'll generate the mesh, we'll play around with some local sizings, and then in this particular case, we've only got one body, but we'll start to break it up as well and play around with, what we can do. There's nothing particularly happening in this model, so there's nothing internal. So I can use this section plane to kind of cut through, nothing happening inside there. So on the left-hand side, you can see we've got kind of details of mesh. And if we expand the sizings, there are some global sizings for the mesh here. They'll just try to pick up generally, what the overall size is and what some key features might be, and then it'll try and generate what the appropriate size might be to fix this up, right? So you can see here by applying the general mesh settings, this is exactly what we've got here. We can then go in and we can start to make some changes as well, right? So if I get rid of, let's just get rid of mesh defeaturing, and we'll get rid of curvature as well, and then we'll just slowly try to turn some of these things on and see what happens. So you'll notice the capture curvature, when everything's turned off, the mesh is pretty coarse. And we've got the default element size of around 6 millimeters. We can zoom in, and we've got a little ruler at the bottom to indicate how big something is as well, and you can kind of have a look at that. So we can go into that, we can make it something like 4 mil, and it will globally make everything a little bit finer. Right. If we wanted to capture the curvature, right? So if we wanted to capture these fillets, we can use global sizing here. So if I switch that on, you'll notice we've got a couple of options. So I'll generate that. We can specify what the minimum size might actually be for these curved elements, right? And what the normal angle is. So at the moment, again, minimum size is relatively small, and we've got a normal angle of around 18. What this normal angle is, so I'll switch this over to 9. and generate that again, it'll try to determine, what's the angle at which I can put an element. Sometimes the minimum sizing might be a bit smaller, right? So you can see in this particular case, I didn't change the minimum sizing, but it's now able to put a element, every X amount of degrees. Right, and you'll generally start to find, the finer and finer that you get, the more elements you'll start to pick up, and you'll start to, pick up the flow features around there. And if we have a look at, the statistics a little bit later on, we'll find that we've got a finer and finer mesh as well. This is probably going to take a bit too long, so I'm just going to hit the stop button at the bottom here. We'll switch this back to 18, and we'll just generate it. So you'll notice on the left, we've got how many nodes and how many elements. So every time we update it, we'll be able to see what's happening around that region. And if we go to, we'll just have a look at quality, we can have a look at the quality metrics, right? Because we've got these tetrahedral elements, we'll use skewness. Actually, what we'll do, we'll keep with orthogonal quality just to be consistent between Ansys meshing and Fluent meshing as well. So when we specify, we can pick up quickly what the minimum, max, the average, and the standard deviation is, and we've got this bar chart. And if we select anything, we can actually identify where those elements are, right? So if I have a look at the very bottom here, I can try and click on those elements, and you can see exactly where we've got our poorest quality elements. I mean, that is still very good, right? 0. So 0. Below 0.1 might be a problem, but in this particular case, this is entirely appropriate, right? What we'll do as well, so we'll click out of that. I want to show this defeaturing as well. So you can see in this particular case, I've got some geometry around this region, right? I haven't gotten rid of it in the geometry. You can absolutely do that as well. But what we can do is use this defeaturing size to get rid of those these circles here. So you can see here, they're roughly around 3 mil. So let's just say we make the defeaturing size around 4 mil. We'll have to increase our mesh size a little bit. We can hit generate, and you can see it gets rid of those. So it doesn't respect those elements around there at all, the edges around there. So we'll turn this off though, and then the next thing that I wanted to show you as well is proximity. This might not be the appropriate one for proximity. Just make it a bit larger. Right, so what proximity allows us to do is it allows us to capture elements between certain components, right? So what we'll do, maybe I'll make a small example and we'll have a look at proximity a little bit later on as well. The other thing that I wanted to show you guys now is, so we will turn proximity off and we can generate the mesh. So these are all the global sizes. So you can see everything is being affected. What we can do though is select certain features and start to refine around there. So if I have my selection filter set to my face, I can click that, right click, insert sizing. All right, and then in here, I can then start to generate a specific size. So let's say I want a 2 mil sizing. If I change that to 2 mil, by the way, you'll notice that my cursor and the little dot changes as well. So, it indicates how large roughly 2 mil is. Let's make this 1. And we'll hit generate. Right. So what we can do is we can refine locally around spaces depending on what we wanted to do. Right. So if I take a section plane through there, you'll notice it's just the faces around that region and the elements out are refined, whereas everything else like down the middle is still relatively coarse. Right. It's still at a 4 millimeter level that we specified before. Right. So if there are any problem elements, one of the things that I might do, and you can see the mesh sizing has changed a little bit, I might go in, identify, where we've got problems around here, and then start to implement local sizings around some of those regions as well. When you apply a sizing, you'll notice in the advanced, you can actually specify, curvature or proximity locally as well. So what you can do, right, and again, so what we can do is maybe turn off curvature globally, right? And maybe we can leave on a 1 millimeter sizing and capture curvature locally as well. So what we'll see, right, is So on these particular elements, we've got, probably 1 millimeter elements, which is what I've specified. And we've also specifying, capturing curvature around those regions. And you'll notice again, the face sizing at the top, again, is very, very fine, exactly what we're after. Whereas everything else can be pretty coarse as well. Right. So apart from, face sizing, we've also, you can actually pick up the edges as well, right? So let's just say we go into here, we wanted to give it sizing. Instead of element size, I can actually specify the number of divisions, right? So I can actually make sure there are, say, 20 divisions across some of these edges, right? And again, right click, hit the generate button and allow us to do that as well. Right, and again, I can go in if I wanted to on the mesh level, again, specify edge sizing, and let's just say I want 10 elements to capture the circle and the elements around there, right? So depending on exactly what you're trying to refine, you can use your global sizings on the left, as well as your local sizings, right, to pick up what's happening around some of these regions. In Ansys meshing, we can do a couple of things here to change mesh sizing as well. So we'll talk about that. Before we do that, actually, one thing I will show you as well is, so we'll have a look at the method in a second so we can change the actual mesh type. We can also change contact sizing if we've got certain regions. We've got a couple of additional controls in there as well. I'll also just show you guys how to specify things like inflation as well. So let's just delete these. And we'll just set curvature back on. And what I'd like to do is specify that body, right? And I want the boundary that I'm applying this to. So if I select this face and I'll go Shift F2, or if I use the extend feature here, I can extend to limits. It'll select all those features. We can see the inflation options. I've got a couple of different ones. I'll just leave it as smooth transition at the moment with the default sizings, and we can hit generate. Right. You'll notice we'll have more elements in there as well. And if we take a section plane through the middle, you can see here we've got our inflation elements, right? So we've got these prism elements growing, and that allows us to better capture the actual boundary layer as well. Right, and again, you'll notice on the left where we've got some of these circular holes, again, we've got finer elements picking up what's happening there. So if we're using something like a smooth transition, we've got 5 layers and we'll always leave the default as is. If I wanted a smaller transition, so I wanted smaller elements, one of the things I can do is go in there and start to play around with things like the transition ratio. Right, or I might go in and, maybe because of what I'm after, I might need more elements in there to capture the actual boundary layer, right? So I can then start to play around with that as well. If I ever override something, I can always hit 0 and press enter, and it will switch it back to the actual defaults. What you'll find is generally adding inflation will, you can see here, it'll reduce the mesh quality by quite a bit. And again, by switching and selecting that component, you can again see exactly where you've got these poor quality elements, right? So this is something we probably want to make sure this is above 0.1. So we want to focus on some of these areas to understand why is it bad, why is it quality bad, and what can we do. And you'll notice at the top here again, because the boundary and the face we've specified just here, it's doing what's called stair stepping. So it's slowly stepping down and down until we have no prism elements around any of these regions. If I wanted to, I could also add these two, right? And you'll notice around this region, right, we'll have better mesh quality because now instead of stair stepping, it's able to actually turn that corner and come around, and we've got mesh elements all the way up there. And looking at the mesh, again, we can see now we're above 0.1, which is what we're after, right? But by doing that, you'll notice we've got more elements in there as well, right? So sometimes there might need to be some things that you can do there to play around with it. And again, in here, we've got different ways that we can specify the inflation options as well. All right. So let's suppress that for a second. We'll just generate what we've got. So the other thing that we can do is that we can use what's called this method here. We can select the body And what I can do is I can specify whether it's a TET or something like a multi-zone or Cartesian as well. We normally don't use hex dominant. It's kind of a bit of an old one. And sometimes what happens, let me generate that mesh for you, is that some of the elements internally can be very skewed, which can cause some problems as well. Right, there are some times where it can fail. You can see, by the way, it's highlighting where it's currently working on, so it's working around that region. Right. So a couple of questions there. How do we know what type of method is appropriate for the shape? Again, there's no easy way to actually understand what's method for, what's appropriate for that. Best way to go about it is doing some sort of mesh study, right? So you can see here what's happened. If I don't show you with the hex dominant, the outside looks really nice. However, if I take a section through the middle, you can see some of the elements in there are very skewed, right? And if we open up the elements, again, we've got some bad quality elements through there. So generally, instead of hex dominant, we'll stick with a multi-zone method. In the background, there are just some algorithms to determine, based on things like the geometry and the edges, the curvature, how can we put more efficient elements in there? Sometimes, you can see in this particular case, there are some problems and it doesn't allow you to actually do it. So the meshing tutorials, by the way, will go through this in a lot more detail. But what I might need to do is specify and tell it that, if you're having any problems, you can put, tetrahedral elements kind of where you need to. And you'll notice here, most of the mesh, we'll try to use as hex. These free mesh elements will be tets as needed, right? So you can see here, we've got these hex elements, right, all the way through here where we can add them. Where we've got all this curvature, it's filled it in with all these tet elements. And then it's able to kind of take that and sweep it all the way across. So we've got a nice hex grid, a nice prism grid through there as well. We can use things like, again, sizing on top of that. So again, I can go in, specify specific sizing on a face, and I can generate that grid. All right. Again, a couple more questions. Treat non-Newtonian fluids the same. Recommend any cases for it. With non-Newtonian fluid, so you'll have to look at the solver in Fluent and make sure you've got the appropriate material properties. But generally, you might treat it exactly the same. So when I say in that particular sense, I want to look at the actual flow features and resolve around those flow features. Because it's non-Newtonian, maybe where I might resolve might be a little bit different. Maybe it's not on the actual surface. It might be in particular regions, right? You want to just have a look at the results and then start to make some changes around there, right? So you notice again that face sizing is making that a bit better, right? Is hex dominant okay for simple cases? Yeah, simple geometries where you're not too fast. If you've got a large thing, hex dominant's okay, but we always recommend don't really touch it. Stick with multi-zone if you can, because you're going to get better elements everywhere. There is also things like a Cartesian option, right? So this Cartesian option might be good if you have 3D printed components, where it will try to just put a Cartesian mesh, everywhere, or if you have things like STLs as well. And what you can do is then go in there, make the mesh a little bit finer, and generate that grid as well. Right. So depending on exactly what you want to do, you can use, these methods here to really refine around some of these regions. Normally, if the geometry is easy enough, it will just stick with, hex elements everywhere. But because we've got these, complex, we've got these curved surfaces, it's going to apply some curvature and it might put some tet elements here and there. What I'd like to do as well is show you, so we've got one component in this particular case. I'd like to make some changes to the geometry and just show you what happens when we've got multiple bodies as well, and also looking at what's called shear topology. All right, so I'll answer some questions. Limitations to multi-zone. Yes, sometimes with multi-zones, if the geometry isn't broken up in a specific way, or if it's very complex, the multi-zone algorithm can have some problems actually creating it and generating a high quality grid. So what we, might want to do is, like I'm doing here, is actually go in, change maybe the geometry or cut it up a little bit. and that way, when it bring it back in, you can play around with it. Prefer to use fully structured meshes in this or in ISOM. Whether you're using this or ISOM is a bit different. I think it really comes down to complexity. Generally, I stick with Ansys because it's very easy. We can get simple geometries out very quickly. ISOM, you're going to spend a lot more time trying to generate a high quality grid. So you really want to ask yourself, how much experience do you have with ISOM? How much do you need? Some of, for instance, like our clients, like some defense clients that have very large grids that are running large transient simulations, that are looking for transient les type structures. They will spend weeks generating high quality grids using something like ISOM. Right, and in that particular case, that's appropriate because their simulations are running for days on ends. Right, a 1 or 2% gain in efficiency here and there on a simulation that long is very worth it for their particular cases. So, can we define types mesh locally? Yep, like switching posh to heli in one element. So Cindy, yes, we can. No, we can't quite do that at the moment. So we can't just switch from a hex to poly in a one element. Either we're using kind of tet elements or we're using poly elements, and then the formulations for the hex core and poly hex core, it will determine where it splits from one to the other. We can't use hex core or poly hex core in Ansys meshing. We'll use that in Fluent meshing, which I've got an example for a little bit later on. So what I wanted to show you here is an example where we've got 3 separate geometries. And because we haven't really told anything, we've actually got 3 separate geometries and they're not connected at all, right? So you can see the interface between these 2 regions can be bit, they're not really attached whatsoever, right? That can sometimes be a good thing. That can sometimes be a good thing because in this particular case, because these are nice cylinders, we can very easily specify, how many. You can see you've got a nice swept mesh across there. I can give it inflation. I can go in there and specify how many elements I want across there. I can cut this up if I need to. And the benefit is that I know it's not going to affect the rest of my geometry, right? The problem can sometimes be, though, is that if I need everything to be connected, right? Like if I've got inflation, that can be where I've got some problems that come up. In this particular case, so if I do want to add inflation back in, I can now add inflation, say, just to that component. I'll select all of these geometries. I'll put this back to 5, and then I'll be able to generate a inflation grid all the way across there, right? And we'll just have a couple more elements across here, where we previously didn't have that as well, right? So this is, there are benefits where you've got 2. What will happen though is that you've got some interfaces across there, and if the mesh, is too coarse, right, or there's a large mismatch, we can actually have some interpolation problems through there as well. We can have some reductions in our accuracy, right? So what we can do if we've got geometries that look like this is if we go to Workbench, we can apply what's called shared topology, and shared topology will actually share the nodes across that surface, right? So if I go back in, I'll update the geometry from the source. You'll notice the icons change a little bit. It kind of comes into one component, and we've got a couple of things in there. And if I suppress that, what you'll notice now is if I generate the mesh, similar to before, everything's now connected though, right? So I've still got kind of a swept grid at the top and at the bottom, but what's happening is that the elements are actually lining up, right? The other benefit of doing something like this is that I can progressively make certain components. So let's just say I clear the data. Using my body selection tool, I can select just the biggest body, generate the mesh there, right? And now what it's going to do, it's going to take that face and all those elements and sweep it up that the top cylinder there, right? So you can see it's taken that face, if I put it up, and if I hide that, it's taken the elements on top and just swept it all the way up, right? So it also means if I just hide that, I can, specify that and give it a local sizing. Let's make this a little bit coarser. Let's regenerate the body here. Right, so we've got some coarse elements across there. And then we can regenerate that at the bottom, and we'll have some larger elements, at the bottom there compared to the one at the top. So you can play around with some of these things as well, right? The other thing, like you saw there, what you can do with these multi-body components is that you can specify meshing order as well. So you can first mesh the elements at the top if that's what you're really interested in, and then using the mesh that's generated there, you can mesh the body in the middle. Right, so maybe you're interested in what's happening specifically around these regions. You've got some very fine flow structures, and maybe you've got inflation on here, and you want to be able to just take that mesh, right? So again, another thing we can do, again, clear that generated data. We can fit inflation to the body at the top, right? Again, generate the mesh just at the body at the top, right? That way, again, we've got a good quality mesh around there, and then generate the body, the main body. And in this particular case, actually, if I wanted to, I could even specify a separate method for it, right? So let's go with just a Cartesian. I can't go with Cartesian because I have to specify everything for Cartesian. Or you could just go in and say, hey, let's give it a method, and you can manually give it a different method if you wanted to, right? In this particular case, the multi-zone, it's already going to be sweeping it, so it's already going to be creating, nice elements across there. So that's not too much of an issue. So hopefully this simple component is giving you a good example, good idea about how you can play around, how you can add things like local sizings, how you can add global sizings, looking at your mesh metrics, looking at where you've got good and bad quality elements, and some strategies around fixing it up. And then if you need to change the actual element size, how you can use methods to apply different types of mesh topologies, and how using things like inflation to create prism layers to capture up, to capture certain flow features as well. Right. A couple other questions we'll go through. But retain non-conformal. So can I use assembly meshing but retain a non-conformal boundary condition in Fluent? So I'm assuming you want to assemble it like this and have a non-conformal boundary. I mean, yeah. I mean, if you don't have shared topology turned on, you can have a non-conformal grid. Generally, though, you want to have a conformal grid because interpolation between elements can sometimes be a problem. How do you decide how many prism elements to use? That is one of those questions where you'll need to do some sort of study. Again, if you've got something like this, depending on the actual boundary layer, the flow physics, if you've got thermal effects, if you've got just flow pressure, or if you've got multi-phase flow, that will determine kind of what's happening, right? So what you might need to do is, again, look back, ask yourself, how thick is a boundary layer? How many millimeters could it be? How many elements do I need to actually capture that? Maybe instead of a total transition, you might want to give it a total thickness instead, right? So you want to specify how many layers that you've got, and then what the maximum thickness might be. So let's just say it's 1 mil, right? And then that might be what you're after and what you're trying to do, right? So really, it really comes back to what is the physics and what's the physics locally around there as well. Is flow just going in one direction, or do you have things curving in and out? Do you have things protruding and then holes coming through? Is the boundary layer, pretty is the boundary layer just intact, or does it all of a sudden get tripped up, and we've got turbulence now all of a sudden that we need to account for as well? Can we transfer mesh from a Fluent mesh model into CFX? Yes, we can do that. There are a couple of caveats behind it. So the CFX solver doesn't like hanging nodes. So if you're using things like poly and polyhex core, there are a couple of things that you need to be aware of. There are some features that you need to throw in there. And the other thing is that CFX doesn't actually allow you to bring in a polyhedral grid. It will actually generate a polyhedral grid in the background for you. But that just comes down to how the solver actually works as well. So if you've got multi-zone that's failed, is there an easy way to pick up what's happening? Sometimes going in and having a look at the more warnings, you can normally right click and you can show, and in some cases you can actually go to the object. It'll give you an indication about when something's failed, what the actual problem is. There's not really an easy way to determine, if it's a particular element, right? And in that particular case, what you might need to do is have a look through the different settings that we've got here and start to play around with the different settings that are actually available, right? And difference between shared topology and partition. With shared topology, so we're enforcing, a shared boundary between the two nodes. I'm assuming if it's partition, so if it's not connected whatsoever, it just again means we've got a mismatch between the two surfaces. And if we've got problems, we can sometimes have interpolation problems as well between there. There are instances where we've got a sliding mesh where we don't want nodes that are actually perfectly aligned. We actually want nodes I still have a similar face sizing, but it allows us to actually physically move the mesh and move it around. Right. Okay, so that's most of the things that we wanted to go over on Ansys meshing. Any other questions about Ansys meshing before moving on to Fluent? By the way, when I open up Workbench, you can bring in the Fluent case. It'll use Ansys meshing here as well as CFX. Right, so this uses Ansys meshing. We've got Fluent with Fluent meshing, right? We can have it as a Workbench component here. And what we'll do is create a geometry and we'll feed the geometry in. I normally use Fluent outside of Workbench as standalone. I've found it to just be a bit quicker, so that's why I'll be teaching you. But the tutorials that I've suggested on the Learning Hub will shows you how to work with inside Workbench and outside as well. Cool. So it looks like no more questions. What we'll do, we'll close all this off. And just to show you guys something a bit different, I'll fire up Fluent meshing. So fault tolerant. All right. So we'll do one water type. All right. So we'll fire this one up. So I've got this geometry here, solid body created. We'll have a look at. So I'll take that file. So in the start menu, I'll just type in Fluent. I'll be able to find Fluent 2020 R2. There have been improvements to 2020 R1 as well, but I think most people are going to be using Fluent. If we're opening Fluent outside of Workbench, this is the Fluent launcher. I've got meshing mode selected on the left-hand side, and I'll normally specify the working directory as well. What happens is that there are files that get generated and things like that, and it's just easier having them all in one place. This is one of the benefits of Workbench. It does a lot of the file management for you, right? So meshing, I've got the working directory set in there. If you go to the learning resources, we've got additional learning resources on the left-hand side. We'll open it up in the meshing mode, and we've got a couple of options as well. So we'll use double precision for meshing as well as solving, and you can specify how many how many cores that you want to actually be using to generate that mesh, and the solver as well. So the workflow is similar, but a bit different, right? So this is Fluent. We had a look at it yesterday. So just get that up and leave that there. Different from Ansys meshing, right? On the left-hand side, we've got a couple of workflows that we'll walk through. So we're going to be using the watertight workflow to begin with. In the watertight workflow, let's just fire up SpaceClaim, and I'll just show you guys the geometry, and we'll play around with a couple of the different settings. All right, so this is similar to the mixing elbow. Well, this is the mixing elbow that we created before. All right, so what I've done with this mixing elbow, I've just suppressed the solid, and I've got a vein in there as well. Right, so we've just got this vein, so we'll just be bringing in the fluid region in this particular case. We can bring the solid regions in as well, and we've also got some name selections, right? So inlet 1 and 2, outlet, and we've got walls on the outside as well. Right, so if we go back to Fluent, We'll import. So we'll go through the steps. At any point, if we want to add specific tasks, we can also do that as well. We'll go through a simple step to begin with. We'll get a mesh and we'll go back and then make some changes. So we'll first fire up the the geometry. So we'll import what we need, bringing in as units. So I'm going to read and write. I'm assuming you mean meshing. So you can read and write. Maybe it might be one of those things we want to have a talk about afterwards. If you're having a problem with your particular model, we'll have a look at that. Yeah, afterwards. All right, we'll walk through the steps. We'll say no to local sizings for now. Similar to Ansys meshing, we can go in though and start to apply things like face, body sizing, curvature, right? But we'll just generate a mesh quickly, have a look at it, and then go back and make some changes, right? So the just untick highlights here. So we've got this component here. We're generating, this is the global surface mesh, right? So we can specify a minimum size and a maximum size. If I select it, they're the size boxes, right? Which means that, you know, when you kind of zoom in with some of these cases, you can see how fine the sizing might be. And again, similarly, if you hit the 10mm one, you can see how big the elements are. Similar to before, we've got curvature and proximity. We'll leave it just as curvature from now. And again, specifying things like the normal angle. If you're ever unsure, if you hit the help, it'll give you a bit of a once over about what's happening here. And the more will take you to the online help as well. With a lot of these things, by the way, there are some advanced options. It can get a little bit hairy, so I'm not going to go through them at the moment. But if you're finding you're running through these things and you're having some problems, let us know, and we can help you out on support. You'll notice at the bottom, we've got this console, and it's just telling us what the solver is actually doing, what the program's doing. So after I've generated that surface mesh, again, so we've got, you know, X amount of skewed elements that are below, they're above, sorry, 0.8. Right, you can see what the average is, the maximum is, and what the face count might be. If you have any problems, this will actually give you an indication. It'll point out that, hey, we've got some problems with skewness, and you can then go in and start to make some changes if you need to. And then it'll also tell you things like the max units and how long it took to actually run it, right? And then so on the left, we're describing the geometry. So in this particular case, we just have a fluid region and we don't have any voids, right? We've got an example where we've got some solid regions we'll look at later on. Fluid boundary walls. So if we have more than one fluid zone, you know, touching each other, do we want where the regions are touching, do they want it to be walls? So no flow is allowed to pass through the wall, or is it an internal where we've got flow through the actual interface? In this particular case, we don't have a lot of things happening, so we can just go share, describe geometry. We can update the boundaries, so we can specify, again, our boundary conditions. So this is why it's important to make sure we've got things named. We can tell it what boundary condition is actually, it actually is, and it'll bring it over to the solver. Because I've named it inlet, you know, it's already picked them up as, you know, two velocity inlets. I've got a pressure outlet and some walls as well. So I'm happy with that. We've got the update regions. So we've got kind of two regions in this particular case. We'll generate both of them and have a look at it. So I think what's happening, if we take this section, we can see there's a fluid region, which is highlighted at the moment. So that's that vein, right? And we've got the outside region as well. So what we'll do, it's just called fluid. We'll just call it as a dead region, so it won't generate the mesh in there. And we'll generate boundary layers, right? So in here, again, we'll leave it as smooth transition, but we've got a couple of different offset methods. And again, looking at the help, you know, it'll give you a bit of a thing. If we go to the more, we'll see what's happening there as well. We'll have 3 elements, transition ratio of around 2.7. And in this particular case, we're going to go only on the walls. We can select specific name zones if we wanted to as well. Boundary, so that's all good. And then we'll go to the volume mesh, right? So the next thing here, this is where we can specify what element. So this isn't available in Ansys meshing. So here we can specify whether it's a polyhedral or a polyhex core. So generate a polyhedral element to begin with, right? So we'll have a look at what's happening. So it's generated pretty quickly. Again, bit of information about what it's actually trying to do. You can see what the actual quality is, right? How long it took, what the minimum orthogonal quality is, and what it looks like. And then you'll notice again, we've got our clipping plane set. So I can, move this kind of clipping plane around and have a look at the actual geometry. And normally you go in and then start to inspect the actual mesh to make sure, is it doing exactly what you expected? You can see here, we don't really have too many elements across there. So maybe we can make some changes to capture what's happening around that region. If I was happy with this, by the way, I can save out the actual workflow and I can give it to someone else and they'll be able to load it back in and then easily have all the actual steps that you've specified as well. So let's go to local sizings. We will set that to yes, and we'll give it some local sizings. So a couple of questions. Tend to use instead of uniform. Why? So that last aspect ratio, I'll show you the last aspect ratio in the next time I run this through. So I'll delete the smooth transition and I'll show you why I personally like that. Right. Highlight good and bad mesh influence. Yes, I can do that as well. So let's go into here and let's just say we want to apply what's called a proximity, and proximity will specify elements between the edges that we've got here as well, right? So we've got these walls, right? So actually, if I unselect that, I should be able to right click and select the actual surface there, and you can see it's already named it just volume. That's because, by the way, I didn't give it a name selection. So in Space Claim, I named the inlets, outlets, and the outside wall, but I didn't actually name that, which is why it's defaulted to this weird name here. So let's give it 3 elements across the edge, right? Again, zooming in, we've got our ruler here. You can use something like, like Space Claim as well. It's roughly 5 millimeters. So minimum sizing around say 0.1 should be fine. We'll add the local sizing, right? And then we'll go through the steps again. So we'll just generate the mesh. Again, we can go to the very bottom and just generate any, we'll go through everything, but I like to go through and make sure everything is exactly what we expected. This allows me again to go in and manually check what I've just done, make sure it's correct. I haven't put the wrong numbers or values in. You'll notice just where we've got an edge, right, between the two edges is where we've got some sizing, right? All over these faces, not much is really happening. It's just growing out to be as large as it needs to. So all this is fine. So that's all described. We can update the geometry there. Those regions all look good. Instead of true and smooth transition, let's just use the last ratio. What this allows me to do, I can specify the number of layers. Let's give it 5. The first height, so this is the first height, and the transition ratio as well. All right, so we'll leave that. We'll have a look about what it's doing. And in this particular case, instead of a polyhedral, I'm going to generate a polyhex core. We'll have a look at that. All right, so if there are any problems, it'll give me some indications in red. Right, and it'll go through the steps of making it. So 1 millimeter might be very, very fine. We'll see what we can do there. So you can see now it's generated a finer grid. We've got more elements. It's converted it to polys, and we've got the hex core region around there as well, right? We can see where we've got these jumps around some of these regions as well. And again, there are some regions where we've just got poly elements, right? It doesn't have enough room to grow to generate these hex elements around these regions. Look, the mesh here is relatively good, but if we did have problems, we can insert this improved volume mesh, right? And we can then start to specify where we've actually got what certain limit that we wanted to actually hit. We can also go to, I think it's display grid, and we can select cells and go quality, and we can specify, what the actual range might be. Let's go from 0 to 1. That one, and we can hit the display button, right? So it looks like we don't have that many elements. 7. There you go. So now we can see as well, if we've got a specific range, we can then visibly see, where we might have some of those regions as well. So that's how we can check them out. Let's just delete that. And the other thing I wanted to do though is let's just go back and revert and edit. Having a look at some of the advanced features, what I'd like to do, there's this avoid 1 to 8 transition. I'll set that to yes. And what that'll try to do is that instead of having those hex elements go from that, very large to very small elements, it'll try to put some poly elements in there, right? Those poly elements generally will have, more of those. So the run times and the efficiencies might change as well. Yep. So, got a question here. Would you recommend using the improved volume mesh if you have a bad mesh quality for the geometry? What I always recommend is try to fix it at the source. So if you've got bad mesh, inspect that region. Sometimes you might need to change the actual geometry and make some fixes to the geometry. So we can go in and make changes in space claim, make some changes around here. We can make this smaller and larger, and then bring it back in. Always try to make the surface mesh the best that you can, right? So I should try and get a surface mesh of around 0.5, and then that will make making the volume a good quality volume mesh a lot easier as well. So you'll notice again, it's around here, now that we've got this avoid 1 to 8 octree transition, instead of this large jump from one to the other, we've got a couple of poly elements in there transitioning through there, right? So for internal flows, generally, depending on what you're after, this is something that you can do as well. Right. So a couple of things I want to go over that I've got in some of my slides here. So we've got the mesh preview that we can have a look at. We've got labels and zones. So a zone, you can see here is just individual surface, right? Whereas the labels actually start to come in from space claim as well. The other thing that we can see here as well is that so the sizing. So going back to the sizings, the sizings that we just use in this particular case were proximity, right? But we've got multiple other sizings that we can actually use, right? In this particular case, you can see here a difference between a face sizing and a body sizing, right? So we're in face sizing on the left, body sizing on the right. You'll notice when you have a look at the surface mesh, the meshes look exactly the same. But when you have a look at the actual volume, you'll notice again, the body sizing is the one that maintains that sizing internally as well, right? Looking at proximity, you'll notice scoping to faces or scoping to edges. Right, when you've got faces, it'll actually try to look between the two faces and put your sizings between there. Whereas on the right, you've just got the edges as well. Similar to before, so Ansys meshing, when you've got that normal curvature sizing as well, you've got more elements that you can have at a smaller angle, right? And then the other thing is body sizing as well. So on the right, we're using what's called a body of influence. So we're selecting the body. And when you look at the surface mesh, you'll notice that the body actually vanishes. And the reason for that is that the body is just used as a region to simplify or to represent where you've got a finer mesh as well. So in something like space claim, all you really need to do is just generate, a region around here. So you can just generate a, let's just say a body that looks like this. We want it to not merge, right? And you can call that BOI just so you know what's happening. And what happens is that when this gets imported in, so let's do this import again. Save that. We'll see, we should see some additional bodies come in. Awesome, so we've got that there. Local sizings, yes, let's go body of influence. I'm going to select that component there, and let's just say I want the sizing to be 5 millimeters, right? So I'm going to add local sizings, right? Proximity is fine as well, it's just generating both of them. Let's just go all the way down to here, and we hit update regions. This is just telling me it's going to go in, generate the surface mesh for me, do all the describe, and do all of that stuff as well. So we'll let that do its thing, go at it. You notice straight away the surface mesh is also finer around there compared to the inlet. We will leave the last trans ratio. Let's just drop this down a bit. And instead of a polyhex core again, maybe we'll go back to just a hex core, just to show you guys we've got different ways, and we can very easily switch the fill from one to the other. We've got some warnings in there. You know, you can open this up and finish first. Can open it up and you can see very quickly what all the warnings are, right? And you can address to identify if they're a problem or not. So you can see here we've got, so this is hex core, so we've got TETs on the outside, we've got prisms, and then it goes to this hex region. All right, we've got that around there as well. And you'll notice that body of influence sizing allows me to have a finer mesh around that region as well. Right. So we've got a question asking about moving mesh and morphing. It's not something we're going to quite cover in this session. I've only got one more thing to cover and then we're good to go. Maybe if you want to send us a message on support, it might be something that I can send you some material for as well. Cool. All right. So any questions on the, oh, by the way, to switch the solution, we just hit the button over here and it'll just fire up Fluent for us in the same window, and we can then start to go set up our actual simulations. Any questions about using the watertight geometry or the watertight method? We've got a fault tolerant method next coming up. Just add it to the chat, by the way. Cool. Everyone's looking all good. Switch over to the fault tolerant workflow. So, all right, fault tolerant workflow, a little bit different. Let's just fire up the geometry and have a look at what we're playing around with first, right? So with the fault tolerant workflow, by the way, yeah, all the tutorials and things like that are available as well, so you guys can go through them at your own pace afterwards. So with this fault tolerant workflow, what we've got are a couple of things. Number one, we've got a bunch of geometries here. All of them are just solid, right? We don't have anything. We don't actually have a fluid region, and we won't be extracting it, right? So if I take that surface, you'll notice again, no fluid region whatsoever. Got a couple of things in here as well, right? So this is just kind of protruding through. There's no hole that's created. And in this particular case, we've also got just this hole here, right? So I'm not going to fix any of these things in geometry. I'm going to assume that, maybe you've just been given this geometry and you can't make any changes to it at all. What has been done is that we've just got a couple of inlets and a couple of outlets as well that have been given some name selections. So let's open this up here. Now, interface is very similar. We'll go through a couple of steps. A couple of these steps, though, will be a little bit different. So first thing we'll want to do is actually import what we're after, right? So we'll import this, and we'll hit the load button. And then when it's loaded in, we'll start to see a couple of different things here as well. Right, so we've got the elements that have come through. So in this particular case, we're just bringing everything in. But if we did specify custom, we can say only bring in some components if we wanted to. So if we had a very large file, we can bring in just what we're after. But in this particular case, we're going to bring everything in. We've got a couple of options. We'll just leave them as standard, and we'll be able to import that geometry, and they'll be created as meshing components. Right, so everything's come in. We'll just get rid of that. We'll be good to go. All right. What's happening, right? So we need to tell the solver what's happening, because depending on what you tell it, we've got different options that start to become available. So this is internal flow at the moment. Yes, we will need to create large caps. Large caps are capping surfaces to actually cap the inlets and the outlets and specify where do we have internal and external regions. In the advanced options, what we'll require is what's called feature extraction as well. So we want to extract some of the features around here and some of those components. So we'll describe the flow. First thing is capping. Again, we've got boundary conditions. All we're doing is just telling it this thing here, which we've specified and called an inlet, is actually a velocity inlet, and it will create a cap, right? So you'll see it's actually generated a surface there and capped it off. And then the rest of these ones here are all pressure outlets. Right. So again, the power of this is that if we don't necessarily have the fluid volume extracted, we can actually do that here. We then want to extract some of these features, right? So at the moment, you can see here, there's kind of no geometry feature around here at all. There's no edge that's picked up. So what I'd like to do is actually select this intersecting loop, and I want to select both of these two edges here. And when I do that, what you'll find is that we've got now this edge here, right? That's picked up telling me, this is where we've got this component. And you'll see why that's important a little bit later on. After we've done that, we want to identify what the actual regions are, right? So we want to say, okay, inside here, and by right clicking, so I'm just right clicking on this body, it's already picked up that it's the main, and the location is by the centroid, and it's telling me, I'm going to tell it, sorry, it is a fluid region. That's exactly what it is. I will then pick this outside region over here, and I will tell the solver, okay, this is actually the outside, so this is a void region. Right. The next thing that we'll want to do is define what's called these leakage thresholds. So what it will do, so let's just change it and move it around. So remember, we've got this, big hole over here. Right. So I actually want to tell it, okay, so in this region, we've got a hole and we want to give it some sort of maximum size. So if we actually make the maximum size a bit smaller, we can preview the leakage. Right, so if we make it through Z, let's flip it and let's move it back. So we can actually see here where it thinks is the two distinct regions, and we want to actually cap this up. So what I can do, let's make this a little bit larger. Let's go preview again. All right, let's make it around 6.4 instead, actually. And now you'll notice, right, it's picked up the internal is not connected to the outside whatsoever, right? So we can define the threshold there. Again, we've got a bunch of different options in here, but all we're really interested in is the fact that we can extract this fluid region. We're going to wrap it, and we're going to use the hex core method. And we can use different volume fill methods as well, depending on what we're trying to do. But let's just leave it as hex core for now. We'll leave the default sizings, right? We'll have a look at what it's done, right? So the sizings might be a little bit too large, and sometimes they are, but we'll go back and make some changes to that as well. So by default, again, it'll just look at what the bounds are, so what the extent of this component is, and try to determine. We'll just try to guess what the minimum maximum sizing might be, and we'll just allow it to generate the mesh. Right, so this would be the first pass. Again, a lot of these times when you're doing it, sometimes you may not necessarily know how fine does it need to be. So I always recommend, the first pass should be coarse. Make sure, you can just get it and it can solve. And then afterwards, we can go in and start to make some refinements to the actual mesh. All right, so we'll give it a sec. Awesome. So it's generated the volume for us. Right, so it's removed all those other solid components and then generated that volume for us. Right, you can kind of see where you've got these different components and how it's kind of stitched that mesh together as well. One of the things you'll notice though, right, so it's picked up this volume here. Right, this is exactly what I wanted it to do. Right, so removed that surface in there, but it's a very, very coarse around that region. So what I could do, go back to my local sizings. I'm going to add a local sizing around that region, and let's say we give it something like a 0.2. We can show kind of the size boxes if we select some of those components. That's right. So we'll leave it around 0.2. I normally zoom in and you can see how big 0.2 is, 0.5 actually. And we just leave it as curvature. Add a local sizing on there. Oops, I need to specify the actual pipe. No, actually, I wanted to do it on the main, so I'll have to do it on this object here. The main object. So let's go back to this one. So at the moment, I'm clicking on the surface on the fluid region, which is why it's just complaining a little bit. But I'll select it on the main because that should be fine. Then the other size control that I'll want to add as well is a proximity sizing. Right, so I'm going to add that one to the main, and I'll change some of the settings in here as well, just to pick up what's happening around these regions. All right, so I'll add that local sizing. Actually, what I'll do, sorry, instead of this curvature, let me delete that, and I'll just adjust this one. Right, so instead of 13, I'll make this around 1.5. All right, so we've got that one. We'll just hit the generate mesh and hit that button. All right, so we'll go in and then start to make some changes to the mesh and play around with it. And we'll just allow it to generate. So you can see because the mesh takes, because the sizing is a bit smaller, now the mesh is just taking a little bit more time to generate as well. And because the sizing for the curvature, it'll probably pick up a little bit more, curved components around there. All right, there you go. So it's better captured around some of these regions. All right, got some overlap there. All right, so we'll leave the boundary conditions just as no. And we'll generate the volume mesh as well. And we'll have a look at what the mesh looks like afterwards. So there's a couple more steps in the fault tolerant kind of meshing workflow and the actual process. A couple more things that we needed to actually do. But what it does, it allows us to generate a grid. So you can see in this particular case, so clearly we've made some mistakes. I'll need to go back and figure out what I've done. Instead of making a mesh internally, it looks like it's made it on the outside. So let's go back. So in this particular case, I'd go in, go through and check my region. So I've got fluid region is correct. Void region is correct as well. Yep, that's a void. My leakage thresholds. What I need to do here, there you go, that was my mistake. Instead of putting it on the inlet pipe, sorry, I needed to make sure I got the void region set here. There you go. So now if I go preview again, you'll notice now the outside is the void region and the inside is the fluid region. So that's what we wanted to do. There you go. So let's pick that up. Move it all the way back as well and show you around there. Yeah, so let's pick that up. Okay, that's what I needed to do. Again, we'll go back, update those two things, and we'll allow it to go and generate that surface mesh. We'll check the surface mesh, and then if we're happy with it, we will generate the volume mesh. All right, while that's generating, any more questions at all? Yeah, so I think saw before, moving and morphing mesh, best to have a look at the, if you go to the fluids, go to dynamic meshing, you can have a look at the training material there. All right, so that should have it up. There you go. So we've got some smoothing, some remeshing, some layering inside there as well, using UDF, 6DOF, and the overset meshing methods. Right, okay, so looks like all that is good. Generate the volume mesh, cool. So Angus modeling 3-phase system. Can I do a mesh independent study in single phase? So Angus, I guess that would depend on it. Technically, yes, you could do a mesh independent study on a single phase, but I guess the question that you need to ask is, is there any interactions between the other two phases that you're missing out on that you could potentially potentially need. So you can always try. First thing you should do, you can see by the way the volume mesh that's generated. We've got the hex core through there as well, right? And we've got this region here that's kind of picked up quite a bit. Let's bring this up. Right. Yeah. Yeah, so you can technically do it, but whether, if the physics starts to change quite a bit and you have things like flow features that try to change quite a bit, it might be one of those things that you might need to end up doing in a three-phase system. What you can often do though is just start with a single phase, get that converged, and if you're happy with that, apply that to the three-phase system, and then you can make it a little bit finer and a little bit coarser just to see if there are any major changes to it, and that'll give you a good indication about if you need to do some further refinement or not. So Ahmed, so is space claim design make better meshes in ISIM? So look, there is some meshing facilities in space claim, but I think generally if you're using large complicated geometries, you probably want to be using ISIM and not space claim or any of the Ansys meshing side of things. But that's predominantly only really for structured meshes. If you're new, I always recommend people starting off with either Ansys meshing or Fluent meshing, depending on how complex it needs to be. I only really recommend ISIM if you've got large structured meshes that you have to generate. So from Angus, can you map flow features, course to mesh finder and provide? Yes, that is something that you can do. So maybe you can ask that with Errol. So if you've got a course mesh and you've got it solved, you can export what's called an interpolation file. And instead of initializing the final one, you can just read in the interpolation file. It will interpolate again the pressure, velocity, from the old cell to the new cell, and you can start that off, right? So instead of initializing from scratch, you can go that way as well. Cool. Yeah. All right, so I think those are the main things that I wanted to follow and show you guys what you can do. So hopefully you've seen a bit of Ansys meshing and Fluent meshing, some workflows and some geometries that we're working with. So in Ansys meshing, well, in both, we've got geometries that we can then start to bring in, play around with the sizings. We've got global and local sizings that we can start to add. In Fluent meshing, we've got the additional capabilities of working with different mesh topologies, whether it be polyhex core or hex core as well, and we can also generate polyhedral elements inside Fluent. Now, in Ansys meshing and in the watertight workflow, we need to have the fluid domain that's already extracted. Whereas if we have, dirty geometry or we don't have the fluid volume extracted, we can potentially use something like the fault tolerant meshing as well. The fault tolerant meshing, by the way, if you've got external examples and you've got, say, the driver AIE car, you can use the fault tolerant workflow to actually wrap and generate that grid as well. So another question come in. Yep. So okay. So the question here got polyhex core. So you generated a geometry with 1 mil sizing and another one with around 0.5. Sorry. But both of them turned out to be one sizing. Can you explain what's happening there? Yes, we can. So let me just see if I've got a slide or two on that. That might be a bit easier. So it comes down to the actual hex core, kind of algorithm. I don't have it here. So, because what happens is, even in this particular case, what happens is that the hex core. So if we kind of zoom into something like this, the hex core is around, around 7.5. So it will take the hex core will take whatever the minimum sizing is. So in this particular case, the minimum sizing is around 0.5. Yeah, the minimum sizing is around 0.5, and then it will generate kind of the hex core volumes from there. And because of the way hex core works, right, it kind of doubles in size, right? So one of these elements is one of these elements, right? Well, it's like a 1 to 4. So And you'll find, if the minimum size is say 0.5, so if this is 0.5, the next size up is going to be 1 millimeter, right? So it's going to be this big. And then from there, right, 4 of these will turn into one large element. So if this size is 1 millimeter, the next one's going to be 2 millimeters up. So what I generally try to do is if you've got like an Excel sheet, right, just figure out what your local sizing is, and you're always doubling that, right? So the hex core will try to be as close to, whatever that process is. So I mean, as an example, I'll just open up. Yeah. So if we've got, something that's like a 0.5, and we just kind of multiply it by 2, right? These are the hex core kind of sizings that you've got. So if you've got something that's, you're comparing 1 to 1.5, it's probably going to stick with either a 1 or a 2, right? It's not necessarily going to allow you to go 1.5 unless, you make a change to your minimum sizing, right? Then you can get away with like a 1.5, right? And that's just kind of how hex core works. No issues. So Stefan, surface mesh is not refined. Can you create an erroneous location of flow separation? Yeah, so if you don't have enough refinement around some of your flow features, yes, you can artificially create, separation, and that could just be because numerically you're diffusing what's happening in that particular situation. So that's why it's important to do a mesh study. You do want to be making sure you're really looking around those regions, around those areas of interest, and really refining around some of those regions. So questions about, is it available? Fluent meshing in 19.1. No, 19.1, I don't think it, I think maybe. I don't think I've actually got Fluent that far back at all. I've got up to 19.2. I don't think I've actually have anything 19.2. So I think it was available, like Fluent meshing was available in 19.2. We've been going through the workflow. Previously, though, you just had access to what's called this outline view. Pretty much do exactly the same things as the workflow. It was just a lot more manual labor when it comes to generating these meshes and things like that. So you do have access to that in 19.1. I think if you ever, I think on if you go to the webinars for FSAE, I did have a I had a call that we had with one of the RMIT teams that were using Fluent meshing, I think in 19.1. And I showed them how to use the actual outline view and also how to generate a script about that process as well. Let me, I think it's something here. So it looks like, so solver is this. So I think this is 19. So this is using 19, just walking through all of that, and then generating an actual script. So this script, by the way, is a journal file. The journal file pretty much automates the process of creating an actual creating the actual mesh, and you can use it to also automate the process of creating the geometry as well. So setting up the actual model as well. So yeah, it looks like, I think this is in 19. So you can see the interface has changed quite a bit. Yeah, so I think it is in 19. So yes, I think Fluent meshing is available in 19. You can see the interface has changed quite a bit. So, and the way to go about it is a little bit different. Maybe you can have a look at Leap Australia CFD workflow best practices. And number 12 to number 14, so overview of Ansys Fluent meshing, the scripting there, that process is what you want to do. There you go. The watertight workflow actually came out in around 19.2 as well. So you'll notice the watertight workflow there. I think in 19.2, the fault tolerant was beta, so you may not necessarily see that, or it might be a beta feature. Definitely, what we always recommend is always trying to update as much as you can to the latest versions. There's always a lot of things that change and get improved that go through it as well. Cool. All right. Look, does anyone else have any more questions at all? That's everything that I wanted to go over today. So all the meshing content. Looking pretty good. What I'll do when this is all finished, I'll make sure to download it. I'll throw up a couple of YouTube links, and I'll make a playlist, put it on YouTube, and I will add it to there. And then as every day goes by, I'll try to just make sure that link is up to date as well. Right. So if anyone misses it, I'll try to make sure. I think there was a bit in the morning that I kind of missed out on, but not the end of the world. Oh, read and write. Thanks, Mohammed. What did you want to actually know there? Again, this might be something maybe we take offline. So I think what he's talking about is when you've got something like this, you can go file, read, and you can read in separate components. So you can read in a mesh case file, SARS files, even journal files and things like that. And then afterwards, you can actually write something out as well. So you can write out the mesh file as the actual mesh file. So in the future, if you want, you can import it in. What problem are you actually having, Ahmed, with the read and write? So are you actually having a problem, sorry, or is it just having some problems? Saving when finishing job. Yeah, maybe maybe send a message to support, and we'll have a look at what's happening. Yeah. Priscilla, thanks. Yeah, thanks everyone. Again, the email address for support, I'll throw it in here. support@leapboss.com.au. Right. So if anyone does have any questions, you can send a message through. That should be good. Scripting language for Ansys and Fluent. So the Ansys and Fluent, by the way, is using just what's called the TUI, this text user interface. So everything we can do over here, if I actually select the console and hit enter, you can see all the functions that we've got there. Generally, what I do if I want to do anything, if you can just do a bit of a search for it, and you've got your TUI commands there as well. The video kind of goes through some of that stuff, and you can use, then you can then start to create these commands to and create a journal file out of it as well. So it's not Python, anything like that. It's its own kind of text user interface. Right. There are you can use Python in Ansys. So in the mechanical side of things, you can use that for scripting. And I think there are some additional things that you can do with it, but there's but in this particular case, for Fluent meshing, we were using the text user interface. This workflow, by the way, in the background, all it's really doing is creating these commands, right? And then just reading and writing them back in and out as needed. Cool. All right. Look, thanks everyone for your time. I try to make everything 2 hours, ended up being around 2.5. I hope everyone got a little bit out of it. So tomorrow we'll be starting again, same time, 9 o'clock Australian Eastern Daylight Savings Time. We'll have Errol that will come on, and Errol will start to talk about just an introduction into the actual solver, get into a bit of the numerics as well. All right. Yeah, recordings. I'll make sure when the recording's done, I'll send a link out to everyone. I'll maybe add it to the chat as well. All right, so that should be fine. Awesome. All right, thanks everyone. Look, thanks a lot for your time. Feel free to send some of these recordings out when I've sent it along to anyone. And if you do need any help, the support email's there. So please do reach out to us. All right. Thanks everyone. Thanks for your time. On the meeting now. Bye.